The goal of this project was to implement a reinforcement learning algorithm to develop a policy to perform well at Space Invaders. The baseline metric was to beat the score of the random policy. The first algorithm implemented was DQN. This is Deep Q Learning. This algorithm is centered around replacing a tabular approach to the state space reinforcement learning with the frames and pixels of the images. So the DNN basically feeds into the reinforcement learning algorithm by taking the frames and pixels at each state and training on those instead of just some metrics. We were better able to get this model working, and it beats the random policy consistently. It was improved on by adding mini neurons, as many as possible, to fully utilize the GPU we were using. Also, a replay buffer was added to get the DNN to more heavily focus on the best results received in the training. Finally, a computer vision script was implemented to cut down and reduce the state space so that only the space in front of the spaceship was used. This reduces the number of pixels in the overall space so that there is less unnecessary pixels in the DNN. In the background of the video, you can see a few videos from the game being played by our DQN algorithm. It starts off with the case of the random policy, and it slowly builds up to better and better trained DQN episodes, so the score should be increasing.
As a companion to the DeepQ network algorithm, we implemented Advantage Actor Critic, or A2C, as a baseline. One of the papers by DeepMind shows that an asynchronous multiprocess version of this algorithm performs similarly to DeepQ network. A2C relies on learning from multi-step bootstrap targets. It estimates an advantage function, which is the difference between the value of a state-action pair and the value of that state alone. In our implementation, we estimate the advantage by using n-step returns. This involves estimating the value of the state-action pair as the sum of discounted rewards subsequent to that state action, plus the value estimate for the current state. The policy loss is formulated to maximize the advantage across different time steps. We are constrained by the computational resources available to us, so we trained on 5 runs of 250 episodes. There are many hyperparameters to tune, such as discount factor, weight of entropy regularization, the number of steps to bootstrap with, and the neural network layers. Our agent consistently learned the policy of mostly choosing the fire action during the testing phase. We obtained matching results when training an existing open-source A2C implementation for 100,000 frames. Our training time is significantly less than the tens of millions of frames trained by the papers we are trying to replicate. So if we are to do the same project again, we would give our computational resources constraint much more thought when selecting the model. Nevertheless, the strategy of mostly choosing the fire action causes the agent to outperform the random baseline.
Now in the background of the video, you can see the results. The first results that we had were the reward results, and these are kind of hard to distinguish any clear trend. So if we look at the moving average tests that were done over 10 episodes, you can see clearly the random baseline consistently was beaten by all the different DQN algorithms. But the best result came from with the computer vision and the replay buffer with the large neural network. The same thing can be seen for A2C. In the case of the reward results, there is a trend that shows that the A2C model beat the random baseline, and this can be seen again in the moving average. So both of our models consistently beat the random policy, so we succeeded.